Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, so it's my great pleasure to introduce Nina Naroditska, who's here interviewing for a researcher position in MLP. Some of you might already know Nina because she has been an intern here before. So there we go, all yours, Nina.
Thank you. Thank you for the introduction. I'm currently a postdoc in Carnegie Mellon University, and today I'll talk about SAT-based techniques for optimization and synthesis. So here's an overview of my work. Now I'm mostly working on decision procedures, but I also have a substantial expertise in computational social choice. I did my PhD in constraint programming, and then I moved to Boolean satisfiability, where I worked on Boolean optimization and SAT-based synthesis. I worked on other topics like knowledge compilation, and at CMU I will be working on hybrid systems. In computational social choice, I mostly focused on two directions. I was looking at theoretical properties of different voting rules, and also I was looking at resource allocation mechanisms like fair division, and was applying game theoretic concepts to this problem. But in this talk, I will only cover the first three topics.
Just quickly, what is a hybrid system?
So a hybrid system, it's a system that contains discrete and continuous variables, and also it has nonlinear constraints. So I have a system of nonlinear constraints. They also can support differential equations.
Okay.
The goal of my research is to design efficient algorithms for decision problems. And this is an exciting topic because decision procedures occur in many practical applications like planning, scheduling, disaster management, verification, cancer treatment, and many others. Which means if you make progress on decision procedures, you can make progress in many practical applications. So here's a small wish list that we want our decision procedure to fulfill. So of course we want scalability because we want to solve larger and larger problems. We also want it to be easily accessible for a non-expert user. We often want a complete solution. We want exact solution, especially for safety critical systems. And we want to express as more general problems as possible. But if you look at all these properties from a theoretical point of view, then it doesn't look very good. So even even simple problems, if you look at the worst case complexity analysis, don't admit efficient algorithms. But classical complexity theory is based on the notion of the size of the problem, which can be misleading. So I can easily craft a small problem, and the best SAT solver will never finish. And if you try to compile it using binary decision diagrams, it will just run out of memory very quickly. But if you look at very large industrial structured instances, then modern decision procedures are pretty efficient. So here I put some graphical representations of a number of practical problems like product configuration, model checking, planning, and software verification. And you can see that all these instances have a structure. And decision procedures exploit this structure. Yeah. Yes, so it's given a problem, you have a certain formalization of the problem, and then in terms of variables and constraints, and then you draw a graph where F1 you introduce, there are different ways, but for example, you introduce one vertex for each variable, and you draw an edge if they participate in the same constraint. But you can have other graphs, but this is a standard representation. It's called a primal graph. So structure is a key here. And all decision procedures that I worked on exploit structure in one way or other, which I hope will be clear from the talk. So I'll start with constraint programming. Constraint programming, the idea of constraint programming is to provide the user with very rich modeling language. This modeling language contains high-level predicates. And then the idea is that user, to express his problem, uses these high-level predicates as the building blocks. And then hopefully, when he builds the model or she builds the model, they preserve the structure of the problem in the model. And then this model is passed to a search engine. So constraint programming assumes that the structure is already given to a search engine in the model by the user. So the price we pay for such rich modeling language is that each of these high-level predicates comes with his own inference algorithm. And this inference algorithm has to be very efficient because it's called by search engine many, many times during the search in every node of the search tree, and also has to be powerful.
Can you give an example of one of these high-level predicates?
Yeah, for example, you have a set of variables. Every variable is, can take value from a finite set of values, discrete, and then you might want that all of these variables take distinct values.
Okay.
Or for example, you have another example, you might have a sequence of variables, finite, and then you want to say that solution is assignment that satisfies, that accepted by a certain automaton. Automaton is an input, or belongs to a regular language. So these types of predicates. Inference algorithms focuses on the sub-problem of the original problem. And the goal of the inference algorithms is to filter inconsistent values, values that don't occur in any solution. So there are a lot of applications of constraint programming. I just looked at the list of papers in the application track of Constraint Programming Conference over the last 4 years. There were a lot of scheduling papers, verification, game theory, planning, and other quite exotic applications like constraint wine blending. So we'll look at scheduling. Suppose a user wants to express his scheduling problem. He might want to express labor demand constraints. Another example is regulation rules. If you have employees, you need to build a schedule, and the schedule has to comply with regulation rules. People might have preferences. You might have resource constraints, and so on.
Are these your papers?
Cited, yes,
yeah,
but there are many others.
Okay.
Yeah, so cited are mine. So constraint programming.
These ones here, all yours.
Yeah.
Okay.
Constraint programming provides high-level predicates so that user can easily express these pretty high-level concepts. So let's look at one example. So it is useful in the scheduling domain. Suppose we have a set of jobs. Each job has a release time and deadline. And we also have a precedence graph that defines a partial order of a task. So for example, we know that first task has to finish before second task and so on. So the task of the inference algorithm is to filter inconsistent values, which are called forbidden regions in this example. So what it means, consider, for example, first and the second job. We know that the first job has to finish before second job starts. So it means if the first job starts in the earlier time point, then second job can't start, has to wait because we only have one machine. So in the goal of the inference algorithm is to detect all these forbidden regions. So, and the challenge here was to do it in a low polynomial time, so we showed that it can be done in ND time, where N is the number of tasks, and D is a time horizon. So this is one example of this high-level predicate. Right, so we have this constraint programming that provides this very rich modeling language, but in the other side of the world, we have a SAT, which has very efficient solvers. And for a while, there was a question whether we can simulate whatever constraint programming solver can do, whatever this inference algorithms can do using a SAT solver. And if it would be the case, then CP is pretty much useless because whatever you can do in CP, you can do it in SAT. So it was an open question for a while, and we resolved it at HKI 2009. We gave a characterization criteria that tells which of the inference algorithms, which of these inference algorithms can be simulated by SAT solver and which one can't. And the ones that can are exactly the ones that can be computed by polynomial size monotone Boolean circuit. Otherwise, you will have to be able to simulate it with SAT solver, you will have an exponential blow-up.
What if it was not CNF?
If it's not a CNF, well, of course, we have a certain assumptions on how SAT solver works, what's the inference procedure. So if it's not a CNF, it will be a different story. If you might have weights give you more power. So if it's not a CNF representation that modern SAT solvers accept as an input, then this theorem wouldn't hold. Or at least it needs to be. For example, it doesn't cover weights. If you have weights, you can express exponential. It gives you more expressiveness.
So you are saying that like with PBO you can do a polynomial. With PBO you can probably do this.
With PBO, I don't know. Because PBO it's a linear inequality constraints that have weights, and this is a different story.
How restrictive is this polynomial size monotone Boolean circuit thing? That is to say, does that mean most inference constraint solvers can be expressed this way, or practically none?
Many. But for example, what can't be, all algorithms that are based on matching can't be. So if you have underlying search procedure based on matching.
It's a decent subset, but
Yeah. So matchings, flows, you can't. Okay, next I'll talk about Boolean optimization. So I'll introduce first Boolean satisfiability. Now we are going from very high and rich modeling language to very, very simple and plain modeling language. Now we're only allowed to use Boolean variables and clauses. So here's an example. Clauses are disjunction of variables or their negation. And the goal is to find an assignment that satisfies all clauses. For example, if we can set x1 and x2 to true and x3 to false, then we can satisfy all clauses. Okay, suppose now we have 6 clauses and we're again trying to satisfy them. So we have these 3 clauses a unit. We must set to true x1 and x2 and x3, which makes other clause unsatisfiable. Okay, the problem is unsatisfiable, but maybe the answer, there is no solution, is not really a nice answer. Maybe people are happy to sacrifice some constraints and still get an answer. So this is how maximum satisfiability started. Now we have 2 types of clauses, hard and soft. Soft clauses have weight. Let's say weight 1, and hard clauses don't have a weight. And now we need to find an assignment, but we can violate some of them. But every time we violate, we pay cost 1. And then the goal to find an assignment is minimize the number of violated clauses. So for example, here we might use this assignment, and we will be able to satisfy 4 out of 6 clauses. And this is the best you can do here. So it's an optimization problem. Right, so again, there are a lot of practical applications. I just used applications that were used in the last year competition, which is telecommunications, scheduling, electronic markets, bioinformatics, circuits design, and also at last year conference at SAT, about 23% of papers were related to Boolean optimization topics, not necessarily maximum satisfiability, but optimization version of SAT.
SAT 14 sounds like it's all about Boolean satisfiability, so I'd expect 100% of papers to be about SAT.
No, but all of them were SAT, but not there is a plain SAT where you just want to find an assignment. But in maximum satisfiability, it's an optimization problem.
23% about MaxSAT.
Yes.
Okay.
Yeah.
Sorry.
23% of SAT 14 papers were about related, different version of maximum satisfiability. There are a lot of algorithms to solve MaxSAT, but only a certain class of them perform well on industrial instances, which is a class of iterative algorithms. It's very simple, I'll explain. There are 2 types of iterative algorithms. One is a low bound driven search. We start very optimistic. We say we can satisfy all constraints, which is not possible, so it's unsat. We get a certificate for this unsatisfiability, we relax the problem. We again, suppose we can satisfy every single constraint. If we can't, we relax. So we build a sequence of relaxation until eventually we hit the optimal solution. So dually, we have an upper bound driven search. We start very pessimistic. We can't satisfy anything. So we have very high cost value. We find the solution and we strengthen the formula. Eventually, we build this sequence of strengthenings. Eventually, we'll find an optimal solution. And you can look at a different combination of that. Okay, all these algorithms are based on 2 notions. They're based either on unsatisfiable core or correction set. First, I'll explain what unsatisfiable core is. So unsatisfiable core is a subset of clauses that are mutually unsatisfiable regardless of the rest of the formula. So we look at the first 3 clauses here. It's impossible to satisfy all of them because if you want to satisfy the first and the second one, you set variables to true and then falsify the third one. And it doesn't matter what the rest of the formula is. It's enough to get unsatisfiability. So it's called unsatisfiable core. So dual notion, the correction set.
There may be many.
Many, yeah, many of these.
I mean, any superset of that would also
Yeah,
be.
for example, they might be non-overlapping and they have structure. So, but one core, and yeah, you can define a minimal core that you can't reduce anymore. Okay, so correction set, again, it's a subset of clauses that if you remove them from the formula, the remaining formula becomes satisfiable. So if I remove these three clauses, the rest of the formula is very easy to satisfy. Now, based on this notion, we can build iterative search algorithm. So let's look at core guided search. We have an oracle, which is usually a SAT solver. We give it a formula. It returns the core. We relax the formula using usually this type of linear inequality constraints that has to be converted into SAT. And feed it again, and we iterate until we find an optimal solution.
Sorry, so SAT solvers typically tell you a minimal unsatisfiable core?
No, they give you a core. It doesn't have to be minimal.
Okay, they give you a core.
A core,
okay.
and doesn't
They
have
don't just
to
say
be.
yes or no, they give you a core.
Yeah, you
Okay.
can extract a core.
Okay.
Let's say, but you can extract a core. It doesn't have to be minimal.
Right. And then, sorry, could you just say again what this transform step does?
It does relaxation. It takes a formula, takes a core, and relaxes it. There are different ways how to do it. It's all cost-preserving transformations. I will talk about it a bit later. But the high level introduces variables and linear inequality constraints. So we iterate until we find an optimal solution. Similarly, you can build the solver based on a correction set. You have, again, an oracle. You give it a formula. It returns a correction set. You, again, the transformation. In this case, it will be different transformation. It will do strengthening. And, again, it's based on linear inequality constraints. Okay, there are a few problems with these algorithms. The first problem is this linear inequality constraints. You transform it later into SAT because you use a SAT solver as an oracle, and they're very expensive to transform. They increase the size of the formula, and also the most popular method, they might introduce symmetry. So symmetries that were not part of the original problem. When you introduce these constraints, they become, you introduce new symmetries, which is bad. It makes formula more complicated and harder to solve on the next call to an oracle.
But you're saying slightly different things. So you say, okay, I really understand what it means to increase the size of the formula. Yeah. But in satisfiability, like you said in the beginning, that's not the only parameter that dictates how hard the problem is.
This makes
so
problem
symmetry
hard.
is something that makes it hard for any SAT solver to...
Yeah. So usually if you have industrial problems, it's unlikely you'll have symmetries. But for example, if you use this method, you will introduce symmetries. Because you introduce new variables, and the way it does, it was proven that it introduces symmetries, making problem more and more complicated. On each iteration, you make problem even harder, if it's unnecessary. You might not avoid it, but here you introduce something that you might not need. So the goal to overcome this problem, we use techniques that called MaxSAT resolution, which was proposed about 5 years ago as an alternative approach to solve MaxSAT problem. It's actually a sound and complete proof system that has a single rule. So here's a rule. We have two clauses that clash on variable x. So we have x and negation of x. We resolve. It's similar to general resolution. You get resolvent. But because we're in this optimization world, you'll have to introduce a lot of extra clauses. And it's very expensive. This transformation is very expensive. But if you have...
What exactly is the transformation?
So you replace...
You already have these two clauses?
Yeah, you replace them with this one.
You replace that pair of clauses with this new single one?
And additional one.
Oh, with a whole lot of clauses?
Yeah, so it's TS clauses where S is the number of literals in the first clause and the T is the number of literals in the second clause. And it's proven that you preserve the cost. So it's cost-preserving transformation. It was proven that it's sound and complete rule. So
the reason why you need these compensation clauses is for preserving the cost.
Yes, exactly.
Because with a normal SAT, you wouldn't need them.
No,
it's just
no.
equivalent.
It's just because, yeah. In first of all, normal SAT, you don't have to remove these clauses. So you can resolve and keep the original clause. In MaxSAT, you remove original clause and replace it with this whole bunch of clauses.
It's confusing. The costs don't appear in the clauses?
Yeah, they're all soft. If I put cost, all of them cost 1.
Okay. And you can generalize to
Yeah, you can generalize to different costs. But for simplicity, each of the clause costs 1. Right, so, but if you have a lot of memory and resources, you take your formula, you apply MaxSAT resolution, you obtain a new formula, and you keep going, and it was proven that at the end, when you reach the saturation, you will get a formula that contains as many empty clauses as the optimal solution, and the rest is satisfiable. So you can see it's one way to solve a problem. Apply MaxSAT resolution until saturation, then you just count how many empty clauses you derived, and this is an optimal cost.
And at each step, you get this gigantic blow up.
Yeah, I'm not saying it's practical. Okay. It's just a way to do it. Well, theoretically, you can do it.
And is it obvious which 2 clauses to pick when you do this resolving business?
Well, if you want to be efficient, you have to be careful what you pick.
So you're saying that.
But if you do it to saturation,
You can just randomly pick any 2 clauses
Yeah.
with an X and an X bar
Yeah.
and resolve them, and you
Yeah.
just keep doing that.
until you can't resolve anymore.
Okay.
And then you will have as many empty clauses. The rest will be satisfiable, and you have as many empty clauses as optimal cost. Well, it was very attractive because it's different from the iterative search, but it was infeasible in practice. And people were looking at restriction of MaxSAT resolution with a moderate success. So what we did, we marry iterative search and MaxSAT resolution. So we thought, okay, it's infeasible to apply MaxSAT resolution to entire formula. Maybe we can look at the core, and then apply MaxSAT resolution until saturation, derive 1 empty clause at the time. But it was still too expensive, because if you just apply it until saturation, you blow up. So we said, okay, if we don't guide MaxSAT, if you don't guide MaxSAT resolution, it's not going to work. So we have to guide it in a certain way. And we proposed, given a core, we proposed a predefined sequence of steps that guarantees that you derive an empty core. But, okay, it was better. So if the size of the core was n, we have only quadratic blow-up. But
Choose the predefined sequence?
we proved,
Now, how did you choose it? How does the algorithm choose the sequence?
it does, well, so I define the sequence. It works for any core. And then if you give me a core, I prove that you can apply this sequence. It's the same for every core. And in the end, you will get an empty clause.
Okay.
And you have to prove that it's sound and complete. So, but it was still too expensive because it's not uncommon. You have a course of 1,000 clauses, and if you apply this transformation, it will be quadratic, so immediately you get a million clauses. It's not feasible. Okay, so we observed that all these clauses we introduce share a lot of structure, and we were expired by extended resolution. We said, okay, now we allow to introduce additional variables, and using these variables, we made the compression. And now our transformation is only linear in the size of the core, which was very good. So the algorithm now is very simple. It's the same iterative search, but instead of linear inequality constraints, we use our MaxSAT resolution rule. And we ended the competition last year for maximum satisfiability. My solver is called EVA solver, and there are different 3 categories here. And in one category, it took the first place, and to others, it took the 3rd place. And for example, here it beat even portfolio solver, and other systems were well established, so it worked very well. Why it worked very well, not clear. But for example, it doesn't have problems with symmetries. It might have other problems, but it doesn't introduce the same types of symmetries that other algorithms do.
What are these partial?
So yes, so difference is the following. In case of partial MaxSAT, you have arbitrary weights on clauses. And you can have hard clauses and soft clauses. Here in partial, you can have all soft clauses have weight 1, and the rest is hard clauses. You have soft and hard, and soft have cost 1. And in MaxSAT, all clauses are soft. All of them have weight 1. So this is the most general category because it can handle soft and hard and arbitrary weights. Well, integers. Weights are integers. So we continue work on it, and what was strange to us that we have these 2 algorithms that are not really related, core guided and correction set guided. I worked on this topic with Nikolai Berner from MSR, and we built a new solver that simultaneously can search for course and for correction sets. And then, depending what it finds and applies the corresponding transformation, again, here we had a problem with linear inequalities, which blew up. So we come up with a way exploiting duality between coarse and correction sets to come up with a succinct transformation. And it works pretty well. So here it's a cactus plot. I don't know, do people familiar with this plot? No? Okay, so if we consider a point here, this is one plot for, so we have 6 algorithms. So if we look at this point, it means the corresponding algorithm solve about 860 problems within 1,000 second limit. So if I put 1,000 second time limit, it can solve this many problems. It means that as far right is better. So if we compare last year algorithms, which is this red arc, and our new algorithms, you can see that we get significant improvement by reasoning about coarse and correction sets.
Is this new Z or is this algorithm in new Z?
What's new Z?
The MaxSAT that Nicola implemented in Z3?
Z3?
Yes.
Yeah, he implemented, not this one, he actually implemented the previous one, the last year algorithm. This one, I don't think he has implemented this one. But the one that I talked before that we published last year that performed well in the competition, he implemented in Z3. Right. Yeah, so this work under review we submitted to HKI this year with Nikolai. The last topic I will be focusing today is SAT-based synthesis. Okay, one way to ensure correctness of the problem is via formal verification. You have implementation and specification, and you have a tool where you supply your specification and implementation, and it either verifies correctness of the problem implementation, or it gives a counterexample, and this is an iterative process. So you go through the sequence of counterexamples until you finally get it right. So an alternative way would be to synthesize a program. Given a specification, you synthesize implementation. And then it's nice because it's correct by construction. There were a lot of theoretical work in this area, but there were no practical tools. But things changed. Now people realize that there are a lot of computational resources available, and there are fast decision procedures, and important classes of problems were identified. In the last few years, there were at least 2 large grants given on a synthesis topic. So one is on driver synthesis project, where given a specification of operating system and device, we want to generate a controller, which is a driver for the device. And another project, it's an effort of many universities. They're using synthesis for robotics controllers to synthesize robotic controllers, network systems, multicore protocols, and programming for mobile platforms. So it shows that recently this topic become really very active research area. So one way to formalize synthesis problem is via 2-player games. And I will talk on a very restricted class of games, which called reachability games. So reachability game, it's a game between 2 players, controller and environment. And it consists of 6 objects: set of states, set of moves for controller, set of moves for environment, set of initial states, set of goal states, and transition relation. And transition relation is a mapping from a state, move of a controller, move of the environment, to a new state. So it's usually gigantic, but if in a simple example, we can represent transition relation as automaton. So we have automaton with 5 states. We have initial state, goal state, and every transition is labeled with a pair. The first element of the pair is a move of a controller, and the second element is move of the environment. So given these 2 moves, we move to a new state. And the goal of the controller to reach the goal state regardless of the behavior of the environment. Is it clear? Right. So all current techniques are based on winning state compilation, either exact with binary decision diagrams or approximate with SAT. But BDDs are much better than SAT and state compilation. And I will just show you how modern SAT-based solvers for reachability games are compared with BDD-based solvers using the results of the last year competition on reactive synthesis, which was held in Vienna last year as a part of a sum of logic. So again, it's the same type of plot as a cactus plot. As far right is better, it means you can solve more problems. And there were a number of solvers submitted, and each of them is either BDD-based solver or SAT-based solver. And here I put a line to show the performance, how performance of SAT-based solvers compared to performance of BDD-based solvers. So you can actually see that SAT solvers is the best SAT-based solver for reachability games. It solves about 360 problems, which is much worse compared to what BDD solvers can handle. So currently SAT is far behind BDD, and this is kind of perception in the area that SAT-based solvers don't scale. So
The problem has some kind of structure that SAT solvers are not seeing.
Yes, it's mostly that current SAT solvers, they try to mimic BDDs. They're also trying to do SAT-based solvers. They're also trying to do state compilation with clauses, and it doesn't work very well. BDD is better in compressing. Well, obviously, if BDD solver scales, there is a structure. Otherwise, we wouldn't be able to compile a reasonably small structure. But SAT solvers, from my view at least, they don't do right thing.
They don't do
right thing. They're also trying to do compilation, and they shouldn't. So we want to design algorithms that exploit the strengths of SAT solvers. So we're not going to do state compilation. I'll try to explain what we are going to do. So we were inspired by bounded model checking, and we use SAT for what we call bounded reachability. What it means, we start playing a game, and we fix the number of rounds of the game. So we play a game for 1 round, for 2 rounds, and so on. And suppose when we play a game for n rounds, controller wins, which is a good case for us, because if controller wins in n rounds, we can generate a strategy. But what if it doesn't? If controller can't win in n rounds, it doesn't tell us anything about n+1 rounds, because if you have more time, you might be able to win. So here, we proposed a fixed point computation technique to get the early termination. But I will, in the talk, I will only talk about one step of this procedure. It's a game that we run game for fixed horizon, and we called it bounded reachability. Okay, so now we have a game between 2 players, and we run it for n rounds. We can encode it as a quantified Boolean formula. So here we will use existential quantifier to encode moves of the controller, and universal quantifiers to encode moves of the environment. And then we have a formula that defines the game, which says if we start in the initial state and we follow a transition relation, we need to reach a goal either at step n-1. If we don't manage, then we again apply the transition relation, and we hope to reach goal at n-2, and round n-2, and so on. So you can completely specify reachability games using QBFs. But it's very expensive. So we have a lot of alternation of quantifiers, very huge state space. The transition relation is represented symbolically, and there are a lot of possible moves at each step. So if we take the best QBF is quantified Boolean solvers. If you take the best solver, it doesn't scale at all. So we had to do something about it. And the main yep.
But you have so many alternations. Is this from a specific benchmark? Or?
Well, we run game for n rounds. We have to somehow specify that in each round, one player has a step.
You are encoding that as a single formula.
For example, yeah, well, if you want to encode it as a QBF, this is the way you do it. Because you have to give a choice for a controller at each step, you pick a choice, and you should give an environment opportunity to pick a move. You might have a different formalization, but this is one way.
So there's as many quantifiers as there are rounds?
Yes.
Well, up to twice as many.
It's unfolding for n rounds. You fix an n, and then you unfold.
Okay, yeah.
So the main outcome of this project is, it's still going, but anyway, that we showed that we can build a much more efficient domain-specific QBF solver if we tailor our search for reachability games. Okay, so we looked why QBF solvers don't scale. So first of all, we have a huge branching factor. So in each step, you can have this many possible moves for each player, which is just infeasible. You can't pick. So we have to do something about it, and we propose a domain-specific heuristic to identify. I was told that I have to finish on time, so that's why I'm looking at time. Right. So to identify a small subset of relevant branches. So I will explain our heuristic on example. We have a game between controller, which is angel, and the environment, which is devil. We use green arcs to show moves of the controller and the red one to show moves of the environment, and we run game for 2 rounds. So we start in the root, and we just look at all possible execution of the game. So this is called game tree. You never will be able to build it for any realistic example, but suppose we have really small examples that we can build this tree. Okay, so now we have an angel who is in the root, and he has to pick between A and B, and no information is available. So he has to do a choice. And imagine you might have 2 to 30 possible choices. You have to be really careful how you choose. So what angel assumes and says, okay, I assume that opponent cooperates, so we don't have red arcs anymore. I pick move for myself and for the environment. And then I say I will try to find one way to get a goal. Obviously, if I can't find the path to a goal if opponent cooperates, I will not be able to find the path to a goal at all, so I will lose, right? So, but if I can find the path to a goal, it doesn't mean it's a winning move, but at least it's a good candidate. So he picks A because there is a one way to reach a goal state, and says, okay, maybe A, if I pick A in the first round, it's a good candidate move.
And likewise B. I mean, so this
yeah, it could be here, but yeah.
No, sorry, likewise, path B, yeah, so that would be good too.
Yeah, well,
so
this
just
example.
Says either A or B will do.
Well, I find only one. Okay, in this simple example, you could pick A, B, and actually A was the wrong choice here. But anyway, in general, you won't have that many of them for practical, in practical examples, or you hope at least. So in terms of QBFs, it means that you replace all universal quantifiers with existential quantifiers. So you pick a move for yourself and for the environment. And now you just have a SAT formula. It will give you one solution. And it will be a candidate for the first move. Is it clear? Yeah, now it's a SAT problem. Because I pick a move for myself and for the environment. So, yeah.
So how does kind of what you're doing here in this approach differ from the sorts of things people have been doing in like solving chess for decades, right?
Yeah, you can do chess, but our approach for chess will not scale. Because for chess, you will have to probably look at all possible moves. So we really hope that with when I'll finish, you'll see. We really hope that it's sufficient to consider a small number of possible moves to determine the winner. Because if we're really playing chess, so we are playing against adversary, really clever adversary, then this approach will not scale. Okay, so we have a candidate move, but now we have to verify whether it's actually a winning move or not, and we have a lot of quantifiers. So to build an efficient solver, we here exploit a duality between reachability games, where we want to reach a goal, and safety games. Safety games is a game where you want to stay away from the goal for a certain number of steps. So if we come back to our example, we decide that angel controllable player commits to A. Now we give a move to a devil. A devil only look at this sub-problem, sub-game of the original game and plays the safety game. And the goal of the devil is stay away from the goal. So we play the safety game. Okay, in this case, a devil will be able to solve this game and find a counterexample. Then angel has. So if I play A, devil plays 2, in this example, I can prove that controller loses.
If you explore the whole tree, you're saying there's an efficient way to prove that.
Yeah. So
what's the efficient way? Is it just another call to SAT?
I will code it into SAT. I can build a SAT formula, and then this formula will be. If I play on behalf of the angel, this formula will be unsatisfiable if angel loses. So I construct a SAT formula that encodes this game. So if I continue the search, angel will pick other move and so on, and they'll have other counterexamples. So for example, I collect all these counterexamples and they form a tree. And at certain step, the job of the angel becomes harder and harder. Now, instead of one candidate move, it has to play against 3 of moves from the devil. And it has to reach a goal along all branches of this tree. And this is encoded into a SAT formula. I say devil plays only with respect to his counterexamples that form a tree. So I really restrict devil to play from the tree of counterexamples. And now I'm asking, can angel win if devil plays this restricted game? And they encode it into SAT. It's SAT formula. And this answer to your question is that if this tree is large, like in a chess, I will never be able to build the SAT formula. I can still build it, but it will be gigantic. So we are hoping that just exploring a small number of counterexamples. So this counterexample tree from devil will be small, and then our approach is feasible. So I will solve this SAT formula, and I will have 2 outcomes. If it's a SAT, if it's satisfiable, I will be able to fill these moves here. I will be able to fill this tree. It will be a new candidate tree of moves. If it's unsatisfiable, the devil wins. Yeah, if this tree is large, then our approach doesn't scale. So we call this tree of counterexample abstract game tree. And this is abstract tree because it's only a sub-tree of the original tree. And the question is how to find it. And we use a counterexample guided search to find this tree. So we have a solver that includes 2 competing solvers. One solves reachability game for case steps, and another one solves safety game for case steps, and we maintain an abstract game tree for both players. But we still had a problem. It didn't perform well. It was much better compared to a generic QBF solver, but it wasn't still good. So what actually gave us a really boost, we come up with a domain-specific learning strategy from failures. So basically, if we find a certain state's a failure state for one of the players, we generalize, and then we get a subset of states, which is a failure state. And this worked well. And we published it at CAF. Last year at CAF, we published winner determination problem, which says whether a controller can win or not. And at III this year, we also published an algorithm how to extract a strategy. Okay, we evaluated our approach. QBF solvers don't scale, so we compare with BDD-based solvers, and we compare against the winner of the competition. And our benchmarks come from driver synthesis project. So I use this green arc to highlight performance of our approach, and red one BDD solver. And you can see that the results are mixed. At some instances we were losing, like on top 2 instances we were really outperformed by BDD, and the bottom 2 we were performing better, which I find really nice because current SAT-based solvers can't at all compete with BDD, and at least in some cases we can. And if we add strategy extraction, then it introduces 30% overhead because we use interpolants, which is still very good because competitors might get 40%, 400% overhead. So 30%, it's not really bad. So you might wondering whether it will scale. Well, I'll show progress of our project. We start on one family of benchmarks, so where generic QBF solvers at least can solve some of them. So if we take generic QBF solver, it can solve problems with 30 state variables. And our new solver is also called EVA solver, EVA QBF solver. When we did all these techniques that I just described, we managed to solve problems with 105 variables, which is a significant progress. So we have a now new idea how to perform more efficient learning, and we call it learning via games, and we hope we can get another significant performance boost. Okay, so to answer this question, I don't know whether it will scale, but given our progress, we think it's worth investigating. So we have a lot of work in progress. We have this unbounded reachability and learning via games. Okay, just few more slides on what are next steps. So in my experience with reachability games, it clearly shows that it may be a little bit optimistic if you have a really large problem and you want to take off-the-shelf solver and just solve it. usually, at least in my experience, doesn't work. So I'm not saying that generic solvers are not useful, they are, but to really get a leap in the performance, I believe that we have to look at domain-specific information. For example, if we look at the performance of SAT solvers over the last 10 years, you can see that here's a graph that shows performance of winners of SAT solver competition over about 10 years period. And on the same set of benchmarks, you can see that there were a few performance leap here, and currently area is in stagnation. So there are no significant improvements over the last several years. So how to make a leap? Again, I believe that we have to use domain-specific information. For example, in theory, we know how to make a leap. We have to use extended resolution-based solvers, and those are solvers that introduce new variables on fly. But how to introduce these variables, we don't know. But if we would have a domain-specific information, we might be able to introduce them in the right way and really get significant improvement. Or we might focus on a particular domain, like model checking, and then again build a domain-specific search technique, and people already started to do it for SAT solvers. Similar situation with MaxSAT solvers. We had a few performance leaps over last few years, but again, I don't think we will get much more, like significant leaps in the next few years, unless we will be able to exploit domain-specific information. For example, one way to do it, when we were talking about the course, and was a question about what this course look like. In industrial instances, courses have structure. So this how, if you give me a structure of the course in your unsatisfiable instance, or maybe approximation of it, I will be able to build a sequence of course that I need to look at, and then keep the size of the formula small. So the sequence in which you consider course matter. And if I would know in advance the course structure, I would be able to build this sequence nicely, and then scale and solve larger problems. So the message I just want to convey here is that we really need to investigate properties of domain-specific search procedures in theory and practice. And thank you.
Any questions for Nina?
So, in the course selection approach, if you think about weighted MaxSAT, and some instances of weighted MaxSAT can be converted into MaxFlow, right, into a flow problem.
Wait. MaxSAT isn't be complete, and flow is polynomial. How will
certain families? Of,
certain families.
Right. So, like if you have submodular functions, for example, if you have submodular quadratic pseudo-Boolean optimization problems, right? They are one instance of weighted MaxSAT, and if you when you try to solve them, you solve them using MaxFlow algorithms. And in the MaxFlow algorithms, what happens is you have it's essentially the same sort of technique where you're trying to increase the lower bound, which is you're trying to increase the amount of flow.
Yes.
And how you do it is you essentially find an augmenting path.
Yep.
And an augmenting path is essentially like your core. It is finding certain sort of clauses which sort of don't make sense, and then you pick one, and then you sort of reparameterize, and then you will have some like an empty clause, which is your constant term and your reparameterized term. Okay, but if you look at the complexity of MaxFlow algorithms, the complexity completely changes depending on what strategy you use to choose the augmenting path.
Yeah, okay.
Right? If you use the shortest augmenting path, the complexity is completely different. If you choose the arbitrary augmenting path, the complexity is completely different, right?
Right.
Now, in your talk, you didn't actually talk about how do you choose the unique, the actual core set. You said, well, pick one and then basically transform it.
And now I don't control that. I just call SAT solver as a black box. And whatever it returns me, I keep. I can look at many cores, but I don't control it now. It would be nice to control. If you will tell me what the cores are, then I will be able. I wouldn't need even a SAT solver, but it's not feasible.
So maybe you should talk to the SAT solver people. Perhaps they could deliver cores to you.
No, people talk to you. I will talk to the. I extract. You can't really do well. They have a certain refutation proof, and given this refutation proof, you can get a core. To get a different core, you will need to run different heuristics. So it's not that they give me a core. They have a refutation proof, and from this particular proof, I extract the core. If I want many cores, I have to do something. So it's not that they can select, they can't. It's basically whatever refutation you have, and satisfiability proof you have, this will be a core that I can generate out of it. So they don't have much control over it either. Well, it's possible, of course, if I change the search procedure, I will get different cores, but it's like I'm blind, Why this core is better than other? If I don't have any prior information, it all looks about the same to me. Of course, one preference is clear here, I want minimal cores. A smaller core, because if you have a core, every superset is also a core, and because the transformation depends on the size of the core, of course I want minimal core. Actually, in my solver, I do minimization. Yeah, but currently there is no clever way how to extract core in which sequence, because it's not clear where to look at. Yeah.
So why? So the way you were describing kind of the need for sort of the domain-specific things in this,
yes.
you were saying that you would do things like choose the sequence you were using.
If I would have a prior knowledge, I might be able to find this, to at least guide the search to find. Mm-hmm.
So why isn't this a setting where kind of the portfolio approaches people have been using would be?
Well, portfolio approaches, at least in MaxSAT solving, are very, I would say, simplistic. They have a portfolio approaches for SAT, which have certain static parameters of the formula based on the graph, and then they pick a solver. They're trying to do exactly the same thing for MaxSAT. But static characteristics of this constrained graph, let's say how many nodes it has, what the degree of each node, doesn't really say. For MaxSAT, it's the core structure is the key. And none of the portfolio solvers look at it. That's why they don't perform well. Portfolio solver that has many solvers inside, and my algorithms outperforms a portfolio solver. So it means that they're doing something wrong.
Could you transform what you were doing into a better portfolio solver?
I thought about it, but I didn't. I have some ideas how to do it. Because, for example, there is a clear, first of all, characterization of the problem. Like industrial instances tend to have smaller cores than random one or crafted one. So I think depending, again, I don't know the core structure, but if someone give me average, like a simple feature, average size of the core, I would be able to say maybe for some families of problems, you just encode it into ILP, interlinear programming, and it works well. Not many of them, for some, yes. So it means that if you have a very good linear relaxation and you can solve the problem, then it works. But again, you have to know when to choose which solver. Yeah.
So in your sort of in the whole talk, I mean, there was not much discussion of actually complexity analysis, right? Worst case complexity bounds, of course, are sort of very loose in this sort of case.
Yeah.
But what I was interested in understanding is, have you, especially when you talk about domain-specific information, what are your thoughts on average case analysis, right? Because the types of instances that you see, right, they do not cover all possible types of structures, right? There are only small, there are certain categories of structures, and they're maybe drawn from a particular distribution, and maybe better complexity analysis could be done on those sort of distributions. So.
I agree with you, but the problem is that no one knows what the characteristic for industrial instances. For example, there are a few papers that want to characterize what are distributions that we can generate industrial-like instances, and they were not very successful. So to be able to perform such analysis, you have to first have a clear characterization. What does it mean to be industrial instance? What does it mean to be crafted instance or random? Or pretty much you generate it yourself, you know. So it's not there yet. Well, yeah.
So you pointed to domain-specific information as a way to take the next big step, if you like.
Yeah, I think so.
And I think if I understand right, the thing about reachability was an example of applying domain-specific knowledge.
Yeah.
But it sounded like an example that required, you know, some pretty clever people with brains the size of small asteroids to take that domain-specific knowledge
Yes.
and encode it as an algorithm.
Yes.
What you'd like is a way to say, here's a sort of generic algorithm, and somebody with a new domain could walk up and plug in some domain-specific knowledge that was expressed in a particular way. Do you think we're even close to being able to do that?
No. It's
So
a dream.
It's a new research project for every new domain, is it?
Well, now yes, because okay, I agree that it's a lot of time. It's very time-consuming procedure. You have to really get into domain. You have to understand what are actually features of this domain, and you exploit it. But yeah, that's why there are not that many papers on this, because it's quite a significant time investment. But to be able to do it automatically, if you can't do it manually, how will you do it automatically?
I was thinking the domain expert might have to say something, but maybe the sort of things they needed to say was, you know, give a partial ordering on these kind of things. Say.
Right. Okay. Look, if you think about constraint programming, it's trying to maybe implement what you are saying. It gives this high-level predicates to a domain expert, and he looks at these predicates. Maybe it's a scheduling or whatever, and then it formalizes a problem, preserves the structure, and then maybe search can exploit it. It had moderate success. It's not enough. You have to, because okay, you have these structures, you have this tractable sub-problems that you can really reason efficiently, but there were not enough communication between them. So maybe it's a dream. Eventually we'll get there.
So that's the next big step.
Yeah.
So at the moment it's a whole new research, for every new domain, new research project.
For now, for
Bring
hard
research
problems,
students, throw them into the trenches, and
for now at least, it was, the synthesis project answer is yes. So because these problems are very hard, really huge problems. So, and I'm looking at, it's really restricted class of games where I want to reach goal once. It's far away from what we actually want for synthesis, where I want to reach goal infinitely many times. So, but it's a step. And even this step is problematic, and it's not only for us, it's for the community, because there are no solvers. Yep.
So if you think in the field of machine learning, what has happened is a lot of data, labeled data, has become available, and then that has completely changed the way certain problems are solved.
Yep.
You could imagine the same sort of happening in, can you imagine the same sort of happening in constraint programming or SATs, in the SAT community? You can imagine basically that now people can come up with millions and millions of instances, right? And there is a supercomputer tucked into, say, the likes of Microsoft or Google, which is essentially trying to solve all those instances and then trying to find out what should be, say, the DPLL ordering, right? If I had a magic sort of way to predict the optimal DPLL ordering to reach the solution for this particular instance, right? So can you think about how the role machine learning can play in this?
People did try that, and now it doesn't work.
So
they were trying to build a search procedure, like doing this machine learning analysis, like we'll do probing, run for a short while, and then get features, and it didn't work so far. So
when was this?
like, for example, well, one of the PhD students with my supervisor was working on it, was like about 3 years ago. But if you look at let's look the state of the art. Let's look the best SAT solvers. It doesn't have machine learning inside. It has some scheduling algorithm inside, but doesn't use machine learning. Maybe people didn't find a way.
So do you think the problem is in terms of...
just about done in terms of time. So,
But I just want to say, portfolios do use it. Portfolios are all based on machine learning, but a single solver, they don't use much of machine learning. Maybe didn't find the right way.